Dead stars, known as neutron stars, are incredibly dense. Just like black holes, they bend light due to their presence. But if you think black holes and neutron stars are the ultimate beasts, just wait until we look at one of the most absurd and extreme objects in the universe: magnetars. A neutron star, but, well, more extreme than extreme. But before we can fully grasp what makes a magnetar so extreme, we first need to take a step back and understand what a neutron star is. Black holes, white dwarfs, and neutron stars. What they all have in common is that they're practically zombies, dead stars with a new life. Black holes and white dwarfs have already been discussed on this channel, so feel free to check them out after this video. But in short, a white dwarf forms when a star dies peacefully, while a black hole forms after a supernova, an explosion of a giant star. A black hole breaks the laws of nature. Matter is squeezed so tightly that it bends space-time, creating a singularity that breaks through the third dimension. Traveling to a singularity means traveling to the future. It is in front of you, if you think in terms of time and not space. But when a giant star dies, there can, as far as we know, be two possible winners. If gravity is too strong for the matter, it collapses through space-time and becomes a black hole. But if the matter can hold its ground, it turns into a neutron star. Still extremely massive, but not infinite, because matter is still present in this universe. A star rotates relatively slowly on its own, but when it reaches a diameter of just 20 kilometers, it spins like crazy. This causes two beams to form at the poles, created by the rotation and the ridiculously strong gravity. But where does the name come from? We're made of atoms and ions. An atom, although not the smallest thing there is the most fundamental building block of the universe. It consists of an electron, proton, and yes, a neutron. These particles like to stay apart, but because gravity pushes so hard during the star's death, protons and electrons are squeezed together, turning them into neutrons. But the reality is probably different. Due to the extreme conditions, a neutron star contains matter that is unknown to us and the rest of the universe. This so-called strange matter. If this material were ever to come our way, it would consume all our particles and turn them into the same material. But what makes a neutron star dangerous in another way? If a neutron star were to enter our solar system, the first thing it would do is swallow the outer planets, disrupting Earth's orbit. On Earth, we would experience extreme temperatures alongside radioactive bursts from the approaching neutron star. Once the neutron star arrives, it would also consume our planet. An object as large as Manhattan would tear apart our Earth's crust, with two possible outcomes: the debris crashing onto the surface and exploding, or our planet becoming a ring system. The most massive neutron star ever discovered has a diameter of 20 to 30 kilometers, yet it has a mass 2.17 times greater than our sun. Any less mass, and it wouldn't have undergone a supernova and would have been a white dwarf. Any more mass, and it would have become a black hole. So, mass isn't what makes a magnetar so extreme, but what is? The name says it all. A magnetar is a neutron star with an extremely strong magnetic field. This field decays over the course of billions of years, emitting enormous amounts of electromagnetic radiation, including X-rays and gamma rays. Their magnetic fields are 1,000 times stronger than those of a regular neutron star. A neutron star's magnetic field is 100 million Tesla, while a magnetar's magnetic field is 100 billion to a trillion times stronger than Earth's. This is the strongest magnetic field of any object in the universe. But how can such a magnetar form? During the birth of a neutron star, its magnetic field increases dramatically, but there's more to the story before that. The star that died already had a very strong magnetic field and a rapid rotation speed. This would have led to a so-called convection-driven dynamo, forming during the first 10 seconds of the neutron star's life. If these internal movements align with the star's rotation, the speed is converted into a boost for the already strong magnetic field. But this also affects the outer layer. That layer is primarily made of iron, plasma, and other heavy elements. Before a star becomes a supernova, hydrogen is converted into progressively heavier elements. Initially, it was just helium, but due to gravity, it becomes carbon, then neon, magnesium, silicon, and finally iron. When iron is formed, fusion can no longer take place, and there is no longer an opposing force to gravity. That iron is left behind in the Magnetar and other neutron stars, making up much of their surface. But this surface experiences starquakes, earthquakes, but on stars. These create extreme vibrations that lead to massive outbursts of X-rays and gamma radiation. 1 in 10 neutron stars turn into magnetars, and they're the monsters of the universe. They can be confused with their closest cousins, pulsars. Pulsars are neutron stars with extreme rotation speeds. Their magnetic field is like that of a regular neutron star, but they spin at a rate of 760 times per second around their axis. It's like compressing a 24-hour day on Earth into just 1 second. These extreme speeds cause 2 beams of radiation at the north and south poles. Regular neutron stars have this too, but because a pulsar spins so rapidly, we observe it producing quick flashes, acting like lighthouses in space. That's why discovering pulsars wasn't impossible. Should we be afraid of these objects? The closest neutron star is a pulsar, located 150 to 160 light-years away, which is 1,419,000,000,000 kilometers away. None of them are heading toward us, so for now, we are safe. Magnetars and other neutron stars provide us with insight into the formation of precious metals and other elements. The gold around your finger likely comes from 2 neutron stars colliding in a so-called kilonova. That gold has taken millions of years to reach you. This shows just how precious gold truly is. A massive star exploding and its remnants colliding with another star's remnants, with the leftover material becoming part of Earth. It's incredibly special and gives us insight into how wondrous our world and universe are, and how we, as the intelligent beings of this universe, are privileged to experience it.